molecules that we've looked at so far have not had any lone pairs. But a lot of molecules do have lone pairs on the central atom. When we have lone pairs, then we have to distinguish between electron geometry and molecular geometry. So far, it's been the same. The electron geometry is the arrangement of the electron groups. The molecular geometry is the arrangement of the atoms. So the way I think of this is the electron groups are balloons, right? So we find out how many electron groups there are and make the balloon thing do what it's going to do. And then if we have lone pairs, those are invisible balloons. Clear plastic, clear latex, right? You see right through them. And so the molecular geometry is a description of what we can see. So consider ammonia. Let's look at the Lewis structure. Good grief. Back to back. My ears hadn't stopped ringing from the first one. So if we draw the Lewis structure for ammonia, you done? No. When we count electron groups, that lone pair is an electron group. So we have 3 single bonds and a lone pair. So I already made my balloons into an octahedron, and then I am not taking those apart.
That's supposed to be a 7.
Oh, thank you. Yes, unless we're time traveling. Thank you. So this is what the balloons would do, right? An octahedron. Sorry, tetrahedron. And then we're going to pretend that one of these is invisible. So I took the ball off the end. You could even take this part off too. When that becomes invisible, the others don't move. Because it's there, it's repulsive, but we just can't see it anymore. Okay? So now we're going to describe the thing that's left. Well, it's kind of a triangle, right? But is it flat? It's not flat. Call this a trigonal pyramid, which is different than a trigonal bipyramid, which is 2 pyramids, right? So this is a single pyramid. So here we have the original model. So we have our 4 balloons trying to get away from each other. And then we're going to make one of them invisible. Gone. Right? So we end up with this shape, and that's called trigonal pyramid. So the shape of the electron groups is tetrahedral. The shape of the molecule is trigonal pyramid. Any questions? One of the things I really like about VSEPR theory is it is way more visual than most of the stuff we talk about. You know, you can get balloons and actually manipulate them. You can build models and pull them apart and do stuff, and you get shapes that are recognizable, unlike those weird wave particle superposition things. So a lone pair is actually more repulsive than a bonding pair. And the reason for this is a bonding pair is going to be constrained between the 2 nuclei of the atoms it's forming a bond between. A lone pair is attached to 1 nucleus and nothing on the other side, and so it can spread out. It's going to take up more space. So the ideal geometry for ammonia would be tetrahedral 109.5, but this lone pair is more repulsive to the hydrogens. And so they're going to get a little closer to each other so they can get a little further away from the very repulsive lone pair. It's just disgusting. It's like, ugh, get away. I don't like you, but I like that less, right?
Looks like a ghost.
It does kind of look like a ghost. You don't need to memorize this angle, but with the lone pair there, you should be able to tell me that this is less than 109.5. 109.5, that's just a weird number you got to memorize. 180, 90, 120, those are angles you should be familiar with from geometry. 109.5 probably never came up. So let's look at water. Let's draw the Lewis structure for water. Oxygen in the middle. Hydrogen on each side. And lone pairs on the oxygen. I don't know where that electron came from. How many electron groups on the oxygen? Not two. So this lone pair is a group. This lone pair is a group. This bond is a group. And that bond is a group. 4 groups. What do 4 balloons do? They make a tetrahedron, right? So the electron geometry is going to be a tetrahedron. But now, 2 of those are invisible. They're there. These guys aren't like, oh, they went away. We can make a linear thing now. They're still there. Still repulsive. But the molecular geometry just describes what the atoms are doing. So we've got all these fancy words, and then we call this one bent. So this geometry is bent, tetrahedral and bent. And again, because these lone pairs are extra repulsive, it's going to push the hydrogens together. Instead of being 109.5 for an ideal tetrahedron, they're going to get pushed together even a little more than the hydrogens in ammonia do. But all you need to know is that it's less than 109.5. So, relative repulsion of electron groups. Lone pair to lone pair is the most repulsive. Lone pair to a bonding pair is the next most repulsive, and the least repulsive is bonding to bonding. So how many lone pairs we have is going to affect the bond angles. So here we see with CH4, there's no lone pairs, we have an ideal tetrahedron. Ammonia has 1 lone pair, and so that pushes the atoms a little closer together. Water has 2 lone pairs, and so these guys are pushed together even more than the ammonia. What is the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? So you can either actually draw this, or you can draw it in your mind. So a central atom has 3 bonding groups. So there's a bond, and there's a bond, and there's a bond, and 1 lone pair. That's what the words say. How many electron groups is that? 4. There's 3 bonds and a lone pair. So 4 electron groups, right? What do 4 balloons do? They make a tetrahedron, right? And then one of those balloons is invisible. So what do we call the molecule? Trigonal pyramid. Yeah. So that's this guy. 3 bonding pairs, 1 lone pair. It's trigonal, but it's not flat. If there was no lone pair here, it would be trigonal planar. Five electron groups with lone pairs. So SF4. So all these lone pairs on the fluorines doesn't matter at all for the shape. We're only looking at the central atom. And then this guy has a lone pair on the central atom. Sulfur's big enough, it can expand its octet. Now, where did this one go? There it is. So I have to make a different model now. So we have 5 groups, right? 5 balloons make what? Trigonal bipyramid. There's a trigonal pyramid up here, and there's another trigonal pyramid down there.
When you say 5 group, is it because the 2 or that one lone pair under the, okay.
The lone pair is a group. We don't count the ones on the fluorines because they're not affecting the spacing on the central. We are only looking at the central atom. Number of lone pairs, electron groups on the central atom. So that's going to make this trigonal bipyramid. And then we have 1 lone pair. The trigonal bipyramid is the one that had different angles, right? So if we just pull one off at random, we might get it wrong. So if we put that lone pair in the axial position, that's going to be wrong because now this has 90-degree angles with those bonding pairs. If we put it in the equatorial position as part of the girl's tutu, right? Now it has 120 degrees with these. Still has the 90 here, but it's less, right? Here it had 3 90-degree repulsions, and here it only has 2. So there's more space. So that's going to give us something like this. And then what do you call that? That's called a seesaw. See how it seesaws? Seesaw, seesaw. Teeter-totter, bread and water. Okay, so that's seesaw geometry. Again, we've got the really fancy trigonal bipyramid, and then we've got bent and seesaw. Bromine trifluoride also has 5 groups, 1, 2, 3, 4, 5. Again, single bond is a group, lone pair is a group. So again, we're going to have that trigonal bipyramid, but now we have 2 lone pairs, so 2 of the balloons are invisible. There's more space around the equator, so it's going to be one of the equatorial ones that's going to be the lone pair, because there's more space for them. You know, in my afternoon class, there's like 1 or 2 trains. So, what do we call this? Looks like a T. T-shaped, right? So this is a T-shaped molecule. And then something like xenon difluoride. We've got 3 lone pairs and 2 bonding pairs. So again, we're taking off the equatorial And now we have our ballerina, but she lost her tutu. She's not naked though, because she had a bodysuit on, right? She just lost her tutu. Okay? So then that's linear. Right? Six groups. Now I gotta find my six group one. There's another five. And another five. Oh, there it is. Okay. So bromine pentafluoride, we can see from the Lewis structure here, there's 6 electron groups, 6 balloons, make our friend over here the octahedron. So here's our octahedron. If one of those is a lone pair, all the angles are the same, doesn't matter. Just pull one off. So then we have this shape. And what to call it? Well, if you set it like this, it's a pyramid with a square at the bottom, right? Instead of a trigonal pyramid, it's a square pyramid. So that's called a square pyramid. Because here's this.
Do you remember the Joy-Con?
The Joy-Con?
Yeah. The little thingy where you go like this and you press a button?
Oh, for the Nintendo controllers? I remember, sort of. Why?
That's what that looks like.
Okay. Yeah, I can see that. But unfortunately, they came up with this before Joy-Cons, and so, yeah, we're going to have to continue calling it square pyramid. But that's a square pyramid, okay? Well, let's do more lone pairs. Okay, so here we've got 6 groups again. 6 groups, 6 balloons, octahedral. 2 of them now are invisible. We made one invisible, and now we have to think about, well, where's the other one going to be? The lone pairs hate each other the most of all. So the other lone pair is going to be on the opposite side. Right? So there's our lone pair over there, and then we have a square that's flat. Square planar. Because the balloons, I mean, the atoms, no, the electron groups, there I go, the electron groups, they can shift around like the balloons can't. You know, I could switch and have those 2 pink ones together, right? So if you imagine the balloons, the electron groups shifting around so that those guys can get away from each other. So if these are our lone pairs, they don't want to be near each other. They're like, hey, I'm going to go way over here. I'm trying, can't. There, got away from each other. So then what we've got left is the green balloons, square planar. So this is the table from your textbook, which summarizes all of this. And there's a lot of information in there, but I really don't think we should need this table at all. Because we're going to count electron groups in the central atom. We're going to say, well, what would that many balloons make? Right? Okay, do I have lone pairs? Those are invisible. They want to have as much space as possible. And then we name what's left. And these names are not like random, right? They're pretty descriptive. Imagine that a molecule with 6 electron groups is confined to 2 dimensions and therefore has a hexagonal planar electron geometry. If 2 of the 6 groups are lone pairs, where are they located? So this one looks flat because it is. They're telling us it's flat. So we've got three options here. We could have positions 1 and 2, 1 and 3, or 1 and 4. So this is a lone pair. Where's the other lone pair going to be? It's going to be as far away as possible. Okay? So 1 and 4 would be the answer. So this is a summary. Which statement is always true? Those are always dangerous, according to VSEPR theory. The shape of the molecule is determined only by repulsions among bonding electron groups. Is that true? What if there are lone pairs? Do they affect the geometry? Yeah, they do. That's not true. The shape of the molecule is determined only by repulsions among non-bonding electron groups. That's not true either. The shape of a molecule is determined by the polarity of its bonds. Well, we haven't talked at all about bond polarity today. That's not it either. The shape of a molecule is determined by repulsions among all electron groups on the central atom. If you have more than one central atom, you're looking at each interior atom separately.